Hello, students. Hey, today is our one and only day. You're going to be taking notes this week with this week's topic. Believe it or not, we're going to be done with our notes today. Yeah, that'll leave us more time to play. So if we get done with our notes today, then tomorrow we will play, and the following day we will play as well. So let's get started right away, shall we? So what is this week's topic? Well, hopefully you know that because yesterday you probably watched some introductory videos that were not mine, but those introductory videos talked a bit about acids and bases, and that is our topic for today. Yes, our topic for the week, I should say, acids and bases. So after yesterday's introductory videos, you probably have a pretty good idea of what acids and bases are, who defined the modern definition of acids and bases, our scientist of the week. But some of the information may have confused you a little bit as well. So my goal today is to take all that info that you've been exposed to already in one short day, and I would like to summarize the important stuff for you here today. So let's get to it. Let's begin with the properties of acids and bases, and be sure you are following in your book, and there's a chart in your book that you're going to be completing with the summary information we're going over here right now. So when we talk about properties, remember from earlier in the year when we use the word properties in science, we're not talking about real estate. We're talking about characteristics or qualities of certain substances. You know, my properties or characteristics might be the color of my hair, platinum blonde, color of my eyes, my height, my age, etc., etc. But right now, we're talking about acids and bases. So the first property of acids and bases has to do with something we are not, we are not going to test in the laboratory. So why do we even mention it? Well, stay tuned and you'll find out. And that is the taste test. We are not going to test the taste of anything in the laboratory. However, there is a human sense, which is very closely connected with taste, and that is the sense of smell. You may smell odors in the lab, and I don't mean taking things and snorting odors. That's not what I'm talking about. I'm talking about wafting, not snorting. But, detecting odors, these odors can be very much related to actual tastes. And again, we're not going to actually taste anything here. And I'm just, my little OCD nature. I got to line those words up a little bit better under those columns. But here's the deal. Taste is something that you experience probably every day of your life. And you have tasted things that are either sour, like lemons, or bitter, like broccoli. And you've tasted other flavors as well. But these two flavors here, sour and bitter, are indicative of chemical compounds that make up things that you eat or drink. Let me explain. If you taste something that is sour, chances are it is because it contains acids. Think of lemons for a moment. It's got a high content of citric acid in it. Oranges have ascorbic acid in them. You think of any food that is sour and look at the ingredients, and you will undoubtedly see acids contained in that food or drink. There's nothing wrong with it because your body needs certain types of acids, certain types of acids, because some of those acids contain nutrients that your body possesses and needs to replenish, and also aids in digestive processes. And likewise, with certain foods that have a bitter flavor, like broccoli or kale or uh, spinach, things like that are bitter, primarily because they contain chemicals which are considered basic or bases. So even though we are never going to taste test in the laboratory, you have already taste tested lots of food and drinks in your life, and you are familiar with this property of acids and bases. And as I mentioned, even though we're not going to taste things in the lab, we can still smell things, and odors can be either sour or bitter as well. So there's the first property of acids and bases, and this is really the most tangible one as far as our senses are concerned. The next property is what happens to acids and bases when they are put into solution. There's a vocab word from many weeks ago. You know that a solution involves a solute and a solvent. Well, the solute would be the acid or the base, and the solvent would be water. So if you put an acid or a base in water, it produces something in that solution. And what they produce are ions. Remember learning about ions earlier this unit. Ions are charged particles, charged atoms with a greater or lesser number of electrons, giving it a positive or a negative charge. In the case of acids, if you put an acid in solution, that acid is going to be producing a positive hydrogen ion. Positive hydrogen ion. Now, I'm going to give you a little preview hint here as well, by the way. If you look at the chemical formulas of acids, by and large, they all begin with the symbol H for hydrogen. Like hydrochloric acid, for instance, is HCl. It's got an H in the beginning. You look at the chemical formula for any acid, and it's going to begin with the letter H for hydrogen. That is a clue when we're dealing with acids and bases as to whether you're dealing with an acid or a base. Chances are, if the formula begins with an H, it's an acid, and that H is going to produce a positive hydrogen ion when you put that acid into water. Well, what about bases? Well, bases produce a negative ion, and that negative ion is called a hydroxide ion. It has an oxygen and a hydrogen that is negatively charged. That negative ion, that OH, I'll give you another hint. If you're looking at the formula, chemical formula of a base, chances are if that formula ends with the letters OH, the symbols OH for oxygen and hydrogen, chances are it is a base. For instance, sodium hydroxide. Sodium is Na, hydroxide is OH. Sodium hydroxide is a strong base. And what happens is when you put a strong base into, or any base into solution, it's going to produce negative hydroxide ions. Now, before we get into the next characteristic, I just want you to think for a moment here, because this is going to be a preview for later in our lesson. I want you to look at these ions, a positive H and a negative OH. I want you to think about the type of bonds we learned about several topics ago and what happens with opposite charges. What happens with opposite charges? They attract one another. Now check this out. H is positive, OH is negative. They're opposite charges. What do you think might happen if they find one another in a solution? They're going to be attracted to one another. Again, the chemistry of love. Ah, yes. So, if you've got a positive hydrogen and negative hydroxide, ions coming together, what do you think forms? Ho, 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 ho. H-O-H. Ho, ho, ho. H-O-H. I want you to think about what that might be. How might you write that chemical formula? Don't say it now. We're going to come back to it later. I've just given you a foreshadowing of things to come. So let's move on in our notes here. Acids and bases are also known as something else. Acids are also known as proton donors. What in the world does that mean? Well, let me try to explain it to you. We mentioned in the previous property that acids produce a positive hydrogen ion. Now think about the periodic table. Think about where hydrogen is. Upper left-hand corner. Group 1A. What does that group 1A mean? How many valence electrons does it have? 1. Very good. So in order for hydrogen to become a positive hydrogen ion, what has to happen with that electron that's negatively charged? It has to go bye-bye. It has to get rid of that negative electron. And so what's left? No electrons. Only the positive. Positive what? Positive what? Proton. That's right. Positive proton. So a positive hydrogen ion is really nothing more than a proton. That's why acids, and I know there's a neutron there too, but we're ignoring it for the time being because we're just thinking of charges. So the only thing that's left is a proton. That's why acids are known as proton donors. And conversely, if you think of bases, we already mentioned how opposites attract in the previous property of what happens in solution. So if we've got an OH negative ion, what does it want to receive or accept? It wants to accept that positive hydrogen ion, which is a proton. So acids readily give up a proton. Bases readily accept protons. That's one of the interesting interplays between acids and bases. One likes to give and one likes to get. Okay? And they work together that way. It's okay. It's not that bases are greedy or anything like that. Acids freely give and bases freely get. That's just the way it is. But there's another property as well that is pretty important when it comes to chemistry. Another property of acids and bases. Acids, when they are in close proximity to or in contact with metals, they tend to react. Now, you know that from earlier this unit. Think about the magnesium and the zinc in the presence of hydrochloric acid. You remember all those bubbles that were produced and the hydrogen gas that was generated by that violent reaction. We know that acids do react with metals. What you may not have known before, however, is that bases tend to be slippery to the touch. Why might that be? Well, we have our skin, and here's a little diagram of our skin, and the upper layer of our skin is called the epidermis. Our epidermis is made of organic lipids, fatty materials that tend to melt away in the presence of strong bases. Yes, if you touch a really strong base in the laboratory and it feels slippery between your fingers, chances are it's because it's melting your flesh away. Ooh, not good. Yeah, so we don't want to be touching acids and bases, especially strong acids and bases, with bare hands. So in the laboratory, we'll be wearing gloves when working with really strong acids and bases. But there's another example of something made with bases that is also slippery, but you don't have to worry about it melting your flesh, and that is soap. Think about it. When's the last time you washed your hands with soap? And I hope it's within the last 24 hours. Please let it be within the last 24 hours. But if you've ever washed your hands with soap, you know that soap is slippery. Guess why? Soap is made with a strong base. Pure soap is made with sodium hydroxide, a very strong base. Now, there's a whole process involved in neutralizing to some degree that strong base, but soap tends to be slippery to the touch, and so do strong bases. So be careful in the lab. Be careful in the lab when dealing with strong acids and bases. So now, how are we going to be able to figure out which one is which in the laboratory? Well, there are certain indicators that we're going to be using in order to determine whether something is an acid or a base. Indicators. Do you remember indicators? Let me give you a little reminder of indicators. You know, if something fizzes, then a gas is being released, and gas being released is an indicator of a chemical reaction. And sometimes those gases can form an aroma, an odor. If you smell something, it might be an indicator of a chemical reaction. If there is a replacement of one element for another, then we might see that dramatically with color changes or heat being released, like a temperature change, whether it's absorbing or releasing heat energy. If there's a new substance being formed entirely, these are some of the reminders here of indicators of chemical reactions. And perhaps with this acronym, this mnemonic, maybe it'll help remind you of some of the indicators that you should be observing as to whether a reaction is taking place or not. I'm sure some of you will really enjoy that mnemonic aid. Just please don't take it literally, if you know what I mean. All right, so what are some specific indicators of the presence of an acid or a base? Well, over the next 2 days, we are going to be playing around with experimenting with acids, bases, and indicators. And we're going to be determining whether solutions are acidic or basic. And the most basic type of indicator is something called litmus paper. In fact, you may have used litmus paper in previous years to determine whether something is an acid or a base. Now, our activity tomorrow is going to be further explaining litmus paper, so I'll stay tuned for tomorrow's activity and I'll explain in greater detail the usage of litmus paper. But know for now that there's red litmus paper and blue litmus paper, and litmus paper turns red in the presence of an acid, and it turns blue in the presence of a base. Blue base. Blue. Blue base. Maybe that'll help you remember the blue and the base. All right, next indicator is something that I love to say. It's one of those cool science words, and it is called phenolphthalein. Say it with me, can you? Phenolphthalein. Oh, that is just a cool science word. Let's look at it. The PH is pronounced as an F. Phenolph. Everybody say phenolph. One more time. Phenolph. And then the second part of the word, the TH, phthalene. Phthalene. Say it with me. Phthalene. And now put it all together and you've got phenolphthalein. Say it one more time all together. Phenolphthalein. Yeah. Well, phenolphthalein is an indicator that remains clear in the presence of an acid, but turns a pink color in the presence of a base. This is going to be really important info over the next couple days, so be sure to write this down. Phenolphthalein turns pink in the presence of a base. And it's, some people might call it pink. Some people might call it fuchsia. Some people might call it, I don't know, some other fancy name, but we're just going to call it pink. Next. The next indicator of an acid or a base is pH paper. pH paper comes in a variety of kinds, but basically pH paper will turn different colors in the presence of an acid or a base, but more than that, a pH paper will give you a range of colors indicating a range of values of just how strong or weak an acid or a base is. So with pH paper, you match up the color to a number, and the numerical value of an acid will always be less than 7, and the numerical value of a base will always be greater than 7. So you're looking at the numbers that correspond to the color of pH paper, and that will tell you whether it is an acid or a base. So less than 7 is an acid, greater than 7 is a base. Now I mentioned this pH to you. I want to expand on that for a moment, if I may. pH. Notice the capitalization. Lowercase p, uppercase h. pH essentially is a measure of the concentration of hydrogen ions. Hydrogen ions, positive hydrogen ions. So the H is pretty clear. The capital H refers to hydrogen ions. But what about the lowercase p? There's a lot of controversy and uncertainty as to where the little p comes from. But it's only a little p, so don't get too upset over it. No, I'm just kidding. The lowercase p, I have heard it said that the little lowercase p actually is reminiscent of the Greek letter rho. And the Greek letter rho in mathematics means to propel your boat gently down the stream, doing it 3 times in a row. Row, row, row your boat gently down the stream. No. Rho in mathematics means the concentration of something. So rho H, pH means the concentration of something. Whether that's absolutely true or not, I'm not exactly sure, but that's what I've heard. Now, the pH of something indicates how acidic or how basic a solution is because it measures the hydrogen ions in a solution. By the way, we're not going to get into this necessarily, but there is also a thing called pOH, We won't get into that now, but in high school, I'm sure you certainly will. But pH indicates how acidic or basic a solution is. Again, it measures the concentration of hydrogen ions. And it's kind of a funky, what is called a logarithmic scale. We're not going to get into the mathematics of that, but it is an inverse exponent scale. All you need to know is this. All you need to know is the lower the pH, the more acidic something is. The higher the pH, the less acidic and the more basic something is. So if we look at certain items on this diagram here, we've got hydrochloric acid with a pH of 1. You really can't get too much lower than that. A pH of 1 is super acidic. We got lemons there, pH of 2. Yeah, lemons are pretty darn acidic. That's why if you get it squirted in your eyeball, it's like, oh man, that burns. It's because it's acidic. Vinegar is also known as acetic acid, pretty acidic. Tomatoes, pH of 4. Bananas, pH of 5. What are those? Kiwis? I think they're kiwis. Kiwis, a pH of 6. And look at this, a bottle of water, a pH of 7. Because water, pure water, water with nothing else in it but water, is neutral. It has a pH of 7, right in the middle. Then we've got, let's see, eggs, pH of 8, baking soda, 9, hand soap is 10, ammonia, ammonia is 11, bleach, 12, oven cleaner, 13, and sodium hydroxide, 14. That's a pretty strong base. Again, the lower the number, the more of an acid it is. The higher the number on the pH scale, the more of a base it is. And right smack in the middle is neutral, having a pH of 7. Okay, so I'll tell you what, we're going to end our notes here for the day so that you can review all of this because it was an awful lot. And we're going to save the rest of the notes for tomorrow, actually, because the very few notes that we're going to take tomorrow will tie into our classroom activity that we will be performing together as well. So until tomorrow, we'll say, as usual, bye-bye.